Hey everyone, let's do the Unit 1, Lesson 3 practice in our Desmos curriculum. Today I'm going to be working in the book. Depending on what school year you're watching this video and who your math teacher is, you may have been asked to do this in your book, or you may have been asked to do it online. Make sure you do it in the right spot. The questions are the same either way though, so it should still be like helpful for you to watch this video. I just want to point out that the document camera that I'm recording this on has this weird thing where it makes everything look way more red than it actually is. Like, this is what my hand actually looks like, but here it's very red. And I always feel weird with how red it looks on the screen, but yeah, it's the doc cam. All right, so let's get started. We always have some warm-up questions here. Determine the value of x that makes each equation true. That's just another way of saying, like, solve the equation. What is the solution, or what does x have to equal? Well, here we have 2 plus x equals 1. So this is checking to see whether or not you remember how negative numbers work from 6th grade. So if you want to add a value, but you want your sum, the answer you get after you add, to go down or be lower, you need to add a negative number. So we're going to add -1 to equal 1. So x in this case equals -1. 2 times x equals 1. So here's another tough one to have to think about it. You're like, wait, I have to multiply by some unknown number x, but I want my product, that's the answer you get from a multiplication, to be lower than the factor I'm starting with, this 2. So that means you're gonna have to multiply by something that's smaller than 1, some sort of fraction or some decimal. Well, in this case, it's going to be 2 over 1. I'm just writing 2 as 2 over 1 times 1/2. If you did that, you get 2 times 1 equals 2. 1 times 2 also equals 2. 2 over 2 is a whole. So in this case, x equals 1/2. And so here, thinking about that same thing, we need to multiply this fraction by something to get 1 whole. Well, 1/7, the number they gave us, times 7, right? If you had 7/7, or you can think of it as 7 over 1, would get you 1 whole, because now you have 7/7. So I think the answer to that one is going to be 7, or 7 over 1. And lastly, for all the same reasons, all the same logic we've talked about in the last few, x is going to equal, I don't know why I'm writing x equals when it's right here. It's going to equal 1/11 on this one, because 1/11, if we put it where the x goes here, and then multiplied it by 11, aka 11 over 1, we would get 11 over 11, which equals 1. All right, a lot of the rest of this activity is practicing drawing some scaled copies or scaled drawings, whatever you like to call them. Let me adjust this situation because my book's about to fall off this desk. All right, draw a scaled copy of the figure on the right using a scale factor of 2. So that means that all these dimensions need to be 2 times what they were. I'm going to make my life a little bit easier, and I'm going to label them. This is 3 boxes, 1 box, 2 boxes over here, 2 boxes down here, 1. That one's also 1, but I'm not going to write it because I don't want to make things messy. So that means I got to make sure I start somewhere where I have at least 4 boxes when I draw the bottom, right? I don't want to go off the page. So let's see here. 1, 2, 3, 4. Yeah, I think if I start here, I'll be good. There's 4 boxes. And then I got to go up 2 over here on the left, because 1 times 2 is 2. And then I need to go over 2, right? Because 1 times 2 is 2. So I'm going to the left 2. And then I need to go up 6, because this 3 needs to get multiplied by a scale factor of 2. So it's here. There's 1, 2, 3, 4, 5, and 6. This 1 has to get doubled to be 2. So 1, 2. And now I should be able to just connect. As long as this right here is 4, I'm good, because 2 times 2 is 4. 1, 2, 3, 4. All right, we're good. If you want to be super thorough, maybe label some dimensions here. And then it says, what is the area of the scaled copy you drew? The area is just the space inside. And we can do that just by counting the boxes. Let's see here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16, I don't know, squares. Usually you put a unit on your areas and your perimeters. And then what is the perimeter of the scaled copy? So perimeter is counting the outside. So let's see here. Let's start with, always move 1 space before you count 1 when you're counting lengths. a common mistake I see is students, they put their pen down and they say 1, and then they move and they count 2 when they've really only gone 1 length. So I'm going to start in this corner, but then I'm going to go 1, 2. Wait, I don't have to do all that. I labeled my dimensions. I can just add them up. Let's hear. This is 6 plus 4 is 10. Over here is 2, so that's 12. Here's another 2, that's 14. Plus this 4 makes 18. You got this 2 on the top, which is 20. So it's 20 boxes, square lengths, I don't know what to call them, around grid marks. All right, now draw a scaled copy of figure ABCD. So saying figure ABC means like the shape that is cornered by points A, B, C, and D. And we're going to use a scale factor of 1.5. So everything has to be 1.5 times bigger. That's going to be pretty hard. And some of these, yeah, all right. This one's going to be a little bit of a challenge, but we can do it. So it looks like we can't really call this 2. It's tempting to write a 2 here between A and B, but 2 would mean that it's going through 2 boxes perfectly. And what we have here is that it's actually going through 2 boxes diagonally, and there's some Pythagorean theorem stuff involved there if you really wanted to see how long that length is, but we shouldn't really call it 2. But what we do know is that if it's going diagonally through 2 boxes, so you know what, all right, I'm gonna write a 2 there, even though it's not actually 2, it's 2 diagonal boxes. Yeah, you know what, we're gonna write how many boxes each one of these is going through diagonally, even though that's not really technically correct. It's still gonna help us complete this task. So let's see here. 1, 2, 3, 4. Okay, this one, 1, 2, 3, 4. And this one is 1, 2, 3, 4. All right, so all the other sides are going through 4 except for side A, B is only going through 2. And so really I just need to do 2 multiplications here because my scale factor is 1.5. And so to figure out the new lengths of the copy of this figure, we need to know 2 times 1.5 is 3. So where this 2 used to be, needs to be 3. And 4 times 1.5 equals 6. So all these that used to be 4 are now going to be 6. All right, so I think maybe the easiest thing to do might be to start with this long bottom length here. And I noticed that like the way this length travels is that it's going perfectly diagonally through each box. Like it starts at one corner of the box and goes to the other corner of the next box. That's different from how side B, C, and how side A, D move, right? They don't go from one corner of the box to the other corner of the box. They're going through at a different angle. And so they go from one corner of one box to the corner of 2 boxes away. So there's a different like ratio of left and right movement and up and down movement happening with those. And that's why I think we should start with DC here. So, all right, maybe I should start, it's hard to know where to start. I'm gonna start maybe right about here. And I'm gonna count 6 diagonal boxes. 1, 2, 3, 4, 5, 6, right about here. That's probably a good place to start because it put me right on the edge, meaning I should have maximum space. Let me use a ruler to make sure that this turns out kind of nice, although the paper being folded is making it kind of weird. Okay. Now, I also want side DA to be 6, but see, I'm not going to go directly diagonal through the boxes. It's with these sides, it's always up 2 over 1, up 2 over 1. So let me go up 2 over 1, and then up 2 over 1, and then up 2 over 1. And that's a total of 6 boxes there because each time I was moving 2. So I got this side, and then I'll do the same thing over here. I want to go, but this time instead of up 2 over 1, it's over 2 up 1. See how this is doing this here on this side CB? I'm going up 1 and then over 2 to get to this point, and then up 1 and over 2. So up 1 over 2 one time, up 1 over 2 a second time, and then up 1 over 2 a third time. I want to connect to that dot right there. And I can just connect this last one here. All right, yeah, that was pretty tough, but now we got our quadrilateral that's 1.5 times bigger than that original one we started with. All right, and then the last part of this page, at least, let's see, let me see if I can get this on the screen a little bit better. It says quadrilateral B is a scaled copy of quadrilateral A. Okay, there is no quadrilateral B because they're gonna ask us to draw it here in a second. But the shortest side is 5 units long. Okay, so the shortest side would correspond to the shortest side of A, right? They're talking about the shortest side of B, I think is what they mean to say. We don't see B, it's not drawn yet. But the shortest side of B has to correspond to the shortest side of A here, which is 2 boxes. So if we need to do copy divided by original to figure out our scale factor, right? And they're telling us in the copy, there's a side that is 5 long, and that corresponds to a side that is 2 long right here. And so 5 divided by 2 is 5 over 2, 5 halves, or 2.5, whichever of those is your favorite. And so the scale factor is 2.5. So now we need to make quadrilateral B, and it needs to be 2.5 times bigger than this. Geez, it almost doesn't even seem like we're gonna have enough space to do that. Let's count this bottom side, the longest one. It's always a good idea to start with the longest side because you need to fit your drawing in these spaces, and the longest side is the one that is like the most important to fit, right? If the longest one fits, all the other ones should kind of fall into place. So 1, 2, 3, 4, 5, 6. Okay, so this is 6 boxes long down here. So when we multiply that by 2.5, well, 6 times 2 is 12. So let's do this in pieces. 6 times 2 is 12. And then 6 times 0.5, or half of 6, is 3. So the answer is 12 plus 3, which equals 15. So we need to make this 15 boxes long. It's almost like we need to turn the paper to even be able to make that happen. Oh, I think Mr. Wong is coming in. Hold on, give me just a second. Hey, I'm filming a homework video for tonight's homework, so sorry. No, it's all good.
Right now?
Yeah, I am on camera right now. All right.
Hey, students.
It was indeed Mr. Wong. All right. All right, so yeah, we need 15 boxes here. Now, we don't have 15 boxes right here. Do we even have, like, maybe we flip the paper over. Such a weird way to have to do this. Now my dot cam's all out of whack. If we flip the paper over, do we have 15 boxes going across this way? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, we're gonna have 15. So I'm gonna use like the lowest line that's not the outside line here. And let me mark it off before I actually do it though. I'll start here. That'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So the fact that we had to think about the number of boxes that we needed before we made this drawing, and the fact that we had to come up with this like creative solution of like, wait, I don't have enough boxes right here next to my shape. What can I do? I gotta turn the paper. I gotta draw it differently. I gotta, maybe do it upside down, whatever. That's part of the creativity of math. That's part of the like thinking ahead, thinking of different ways of solving things, and not just like looking at something in like one single, very straightforward manner, and then just getting stuck because like, wait, I can't do it. There's lots of different ways to think about things. Hopefully this works out though. All right, let's figure out what the rest of these sides need to be. So these sides here look like they're the same. So as long as I just handle one, oh, I'm not even on the screen. I was talking about the 2 diagonal sides here. They're the same. So as long as I figure out one, the other one just kind of has to be the same. So it looks like these ones go over 1, up 2, over 1, up 2, for a total of 4 boxes, right? And I need to multiply that by 2.5. Well, 4 times 2 is 8. And then 4 times 0.5, or half of 4, is 2. So we add those together, we get 10. So I need to make a total of 10 box steps by going over 1 up 2. And so that's gonna be 5 steps because each step kind of goes through 2 boxes. So I'm gonna flip my paper back over and I'm gonna start in the corner and I'm gonna go over 1 up 2 5 times. So 1, 2, 3, 4, 5. And I'm gonna do the same thing on the other side because those sides are the same. So 1, 2, 3, 4, 5. Oof. But now I'm worried because according to the math, the top side was supposed to come out 5 boxes long. That was the whole premise of the question, right? The shortest side is 5 units long. And I've gone through this whole process. And I look at where I put these 2 dots up here. If you can see them on the screen, they're only 1, 2, 3, 4 boxes apart. So what did I mess up? This isn't like me being like a teacher trying to be like, can you spot my mistake? No, I've like legit messed something up here and I got to figure it out. Which that's okay too. That's literally part of math. And you know, then the great thing that's happening here is that I immediately recognized that I made a mistake, right? And instead of just like finishing the problem, drawing the line there and then moving on, like I noticed it. I kept what I was doing in mind the whole time, and now I'm like, okay, I have to go back through what I did and see where I messed up. I bet I didn't count these boxes right here. This is supposed to be 15, right? Watch this be 14. I bet you that's the problem. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yep, exactly. So this should have gone to here instead. And then if I did this same, you know, up 2 over 1 process this whole way from that corner, then this dot should have wound up here instead of where I originally had it. And now we're good. Now I can draw this side right here. I can draw this side here. So it's okay to make mistakes, even when you're the teacher. The most important thing about mistakes is like noticing when you do them, if you can, learning from them, right? Paying attention to detail. If you pay attention to detail, you'll catch a lot of your own mistakes. All right, now we're back. We're up at the top of page 19 now. And it says, there's these 2 polygons. A polygon is just it's a general name for a closed shape with like straight sides and vertices. So like a square is a polygon. Any shape that you can draw that, you know, looks something like this, but then eventually closes on itself. Geez, I was off the screen again. That would be a polygon. Poly means like more than one, multiple. Gon, I think in this side, refers to the number of sides. So just multiple sides. So could these be scaled copies of each other? Well, let's do it the way we've been doing in class. Let's make a table that says original and then copy. And then we got our C divided by O column. And we know which sides have to correspond to each other because in order for them to be scaled copies, the shortest side of one has to match up with the shortest side of the other. There's no way for it to work any other way. If that doesn't make sense to you, I want you to just think about it and digest it in your brain for a second. There's no way that like the shortest side from this shape could correspond with the longest side of this shape if they're scaled copies of each other. So 2, 4, 3, 5, 4, 6, 6, 8. And now we know that in order for these to be scale copies of each other, this C divided by O ratio needs to be the same the whole way down. If it is, they're scale copies and that number is a scale factor. If they're not all the same, they're not scale copies of each other and there is no scale factor. So 4 divided by 2 is 2. 5 divided by 3, well, it's not 2, right? This is what, 1 and 1 with 2/3 left over, or 1 and 2/3 remainder, 5/3, however you like to think of it. That's enough for us to stop right there. We have different ratios between side lengths. So no, the ratios between side lengths are not equal. Boom. All right, and now we've got the explore. Sometimes we might ask you to, depending on who your math teacher is and which lesson it is, we might tell you to skip the explore, make it extra credit, because sometimes these are super hard, but this isn't too bad. We got an equilateral triangle and they want us to draw one with a scale factor of 3. So instead of being 2 on each side, it's going to be 6, right? 2 times 3 is 6. So you're starting from here, 1, 2, 3, 4, 5, 6. And so that means this should go to right about here. And then hopefully this is still 6, 1, 2, 3, 4, 5, 6. Yeah, so that wasn't too bad. That was easy. But the main like point of this explore is to get you thinking about this particular shape, because it says equilateral triangles are always scaled copies, right? It doesn't matter any two equilateral triangles you look at or you draw, they will always be scaled copies of each other. What other shapes are always scaled copies? Well, what it boils down to is any shape that its entire like scale or size is determined by one number, then all of those shapes will be scaled copies of each other. So for example, with equilateral triangles, if this is a 2 right here, then the rest of these have to be 2s. That's what it means to be equilateral. All the sides are the same. And so no matter what numbers these are over here, I mean, I guess these are 6s, the ratios between the side lengths will always be the same, because it's always 6 divided by 2, 6 divided by 2, 6 divided by 2. Any shape you can think of where like all the side lengths are the same, or there's only like one number that controls all the lengths around. I'm giving you a huge hint right now by going like this and going like this, will always be scaled copies of each other. And so I'm not going to write the answers in there. I'm going to let you think about it and come up with your own answer to put there. All right.